So, hello again, everybody. I have uploaded this PDF file in the orders already, so you may see it will have only one individual parameter, which is called impulse response of the channel. And actually, this is not exactly the impulse response. This is rather average values of this impulse response. So what it means is that each symbol we transmit is actually experiencing some variations to this impulse response. And accordingly, here, this deviation is specified as the fraction of the average value. So that means, for example, for the first value of the impulse response, which is for everybody 1, that is direct line of sight channel value, yes, this is 1/4. So that means that on average, the first value of the impulse response can change from 0.75 to 1.25, and this value is random in this range for each basically symbol being transmitted. We'll see if this model is good enough during the process of this task. It should be good, but we might want to change something next week too. This is just the easy way to make the model, and we'll see how it suits our needs. So the tasks are to generate signal without noise. So we are not going to add noise at this step, but clearly it's expected that even without noise, we should have a lot of errors. So we'll see how we can do that. And basically, you can imagine that adding noise even will degrade the signal even further. So even without noise, the expected performance isn't going to be good. Yes, anyway. So the other impulse response values, such as 0.25 and 0.25, are basically reflected signal coefficients. Yes, so basically, if we speak about transmitting from base station to mobile device, and we have direct line of sight signal with the value of 1, for example, and we have two objects reflecting our signal, yes, which each of them travels longer distance with greater delay, and this delay is in fact affecting the position. So we assume that this is a shorter path, this path is slightly longer. And this is the first one, the shortest part, which is, of course, direct line of sight signal. So this signal, after reflecting, has 0.25 fraction of its energy only left. Yes, and this also, for example, has this. As I said, these values will change randomly. Again, if we speak about a Rayleigh model, then usually Rayleigh model has this direct line of sight component. Usually, however, for Rayleigh fading channel, we might even experience it very weak or almost gone whatsoever. Yes, so what we are trying to simulate here is more correct to say that this is generalized Rayleigh model. However, we may change some parameters so that we get, I'm sorry, So yes, sorry about that. It was water delivery a bit too early today. So, okay, where was I? So yes, this direct line of sight component usually for Rayleigh channel is not that big as one. Yes, but again, as I said, next week we are going to add some improvements to our program, and this will make more, how to say, uh, realistic Rayleigh channel model. So these are, as I said, average values of impulse response per specific transmission moment. Yes. And these average values are deviating. So that means that if you run your program multiple times, you should get different result each time. Yes, so that's expected. However, in general statistical speaking for this large number of symbols, in all the executions of your program, most probably in all executions of a program, you will have not so good performance, yes, not so good results for uh, the entire constellation of received signals. Well, we'll see that after we finish the program, and accordingly we'll test it by running it multiple times. So, as I said, we make a Rayleigh fading channel model and we make a Rayleigh channel model. Then we display plots of received constellation diagram of received signals. So for Rayleigh channel, we have k value, yes, k parameter that, how to say it, signifies direct line of sight as the greater is this parameter, the greater is difference between direct line of sight coefficient and the remaining components. Yes, so basically we should expect to get a better picture for Rayleigh channel. However, this, well, will greatly depend on random nature of generated numbers. Yes, so we'll see how it goes. Maybe, as I said, next week we are going to make it more deterministic, not so random, so to get more clear results. Yes. And as the last task, we should display the impulse response and frequency response of our basically channels. Yes, basically channels for Rayleigh channel and for Rayleigh channel. So let us begin. We will make a new script in Octave. It will not use any contents of the previous practical exercise. So I'm going to close any unused files. As usual, I am going to save it, starting with some letter. Yes, and avoiding to use white space, function names, and stuff like that. So this is going to be practical exercise 3 code, for example, like this. Again, Octave seems to be more forgiving on file names than MATLAB, but I still wouldn't recommend using incorrect file name, which starts from digit, which has some white spaces, dots, and stuff like that. Yes. So we are going to specify our parameters, which are, first of all, number of transmitted symbols. So this is N capital. N is 1e4. So that notation means that 10 at the power of 4, which is 10,000 symbols. Again, this is number of symbols. Yes, not bits, because as you know, for quadrature amplitude modulation, one symbol contains multiple bits. And we'll get to evaluating bit error rate sooner or later within this course. For now, we are not even going to add any noise, so we'll stick to symbols for this part at least. Yes. Next step is to add impulse response of the channel, or rather than that, average values. So I'm going to use some values which are not duplicating any value of u. So for that reason, I'm just going to use something like that, 0.3 minus 0.2. Well, which is maybe really close to, for example, this one or this one, yes. But again, you need to remember that it will still randomize a little bit, yes, and well, randomness will be different for each symbol. So that's why here in this fourth task, we say about last transmitted symbol, because each symbol will have slightly different impulse response. Yes, and basically because of that, it's difficult to say what was that. However, if we would draw for each of these 10,000 symbols our impulse response, then we would average it out. Then you should get something like this, which has been specified for you initially, right? So that would be average impulse response. Now, what we want to do is to calculate, I would say, deviation from that. And the deviation is already specified as 1 divided by 4. So I'm going to calculate it as hash deviation by calculate hash mean divided by 4. Yes. Next step, I need to calculate, not really calculate, but specify also Rayleigh channel parameter k. So this will be deviation level of impulse response. And k parameter for Rayleigh channel. Well, for example, let us start with value of 2. Rayleigh channel direct line of sight. It's usual to use such abbreviation as loss, yes, which is line of sight ratio. And that's probably most of it, yes, so we can start generating our signal. Again, you can check out the last week's practical exercise. We have been using similar approach, and however, this time we are, well, let's actually try and see if we can find it. EE. So I can see the first and the, here it is. Here it is, yes. So we have been generating the data as the indexes, right? Which is 1, 2, 4. And then we have used these indexes to actually read the constellation point. Today we are going to use slightly different approach just to see that there are different options and all of them are viable. What we are going to do is now to generate real part as either plus minus 1 or plus minus 3, generate imaginary part. So the result of random generation should be any one of these 4 numbers only. No other numbers should be generated this way, yes. And then we are going to make a quadrature amplitude modulated signal just by making real part plus imaginary unit multiplied with imaginary part, right? And the result will be already modulated signal. So we basically how to say, generate already 2 pulse amplitude modulated signals. So how do we do that? For that, we need to do some mathematical, how to say it, mathematical, not really calculation, transforms, yes, for our generated signal. So what we usually do is use a random integer number generator, which is called rand. So let us maybe here, how to say it, develop our strategy, develop our calculation transform, how we should change these random numbers. So we are going to start with generating numbers rand e up to 4 anyway, and let us say we generate 10 values. So we generate 10 random values from 1 to 4. Yes, well, as you can see, this particular time we didn't really generate number 4, so we can generate once more. Yes, now we have at least 1 4. So actually I'm going to save it as x, some data. Yes, so here you can see random numbers, and each time I generate these random numbers, they are slightly different. What I want to do is to map these values so that, for example, 1 corresponds to -3, 2 corresponds to -1, 1 corresponds to 1, or sorry, 3 corresponds to 1, and 4 corresponds to 3, +1 and +3 accordingly, right? So how do we do that? We can actually add and multiply some values to our generated signal to achieve that. So the idea is that we want to have this x market, yes, and what we want to do is to multiply some number a to our x, and then add some number b. And then as a result, we should get this y value. Yeah. So the question only is about these numbers, a and b. What number I need to add and multiply to 1 to get -3. So, well, first of all, let us, well, it's possible to calculate this problem, of course, yes. If we make 4 equations, because we already know that, for example, for some specific value x, so if x is 1, we should get y equal to -3. So that means a plus b should be equal -3. Then for 2a plus b, we should get -1. For 3a plus b, we should get +1. And accordingly, 4a plus b should produce a value of +3 for us. Yes. Then I suppose it is possible to solve this set of equations. However, it's not so simple, probably because it has 4 equations and only 2 unknown parameters. Yes, and because of that, well, I didn't even try to solve this equation. I just found it much easier to actually pick up this number manually. Yes, so what I did is I actually multiplied with 2 each of the x values. So I said that a is equal to 2. Yes, and then I have observed that actually our x changes into double x. Yes, so that would be 2, 4, 6, and 8. Now, we didn't get much far, but if we see this difference, yes, for example, well, the thing is that we need to, how to say it, sorry for that. If we, for example, find the difference between 2 and -3, the difference will be -5. Yes, so 2, not really, -3 minus 2 is -5. Yes, -1 minus 4 is also -5. 1 minus 6 is -5, and 3 minus 8 is also -5. So if I multiply number x with 2 and subtract 5 like this, I will get what I want. Yes, so I have -3, I have +1, I have +3, I have -1, and nothing else. Yes, so let's see if it is what we want and test this. So we are going to generate QAM-16 signal. real part, the way I have specified, yes. So we generate random numbers, integer random numbers with maximum value of 4 and n values. We multiply with 2 and subtract 5 to make them PAM4 signal real part. Similarly, we make imaginary part. This will be imag part. And what we are going to do now is to find a complex value of quadrature modulated signal by simply adding these two components together. Yes, so we will say that this is our basically this is our direct line of sight signal. Yes, so this is as loss, so direct line of sight signal as loss, which is data real plus 1i multiplied with data imaginary, right? So this is QAM-16 signal. And what we want to do now, we will have 10,000 values. So we might run this code and basically look at it. Yes, how does it look? So, right, and we have 10,000 values. Of course, we are not going to watch them through each individually just to see if it is correct. What we are going to do is we are going to count unique combinations, unique values of this signal. And accordingly, we should get 16 unique signals. So let us test it by finding the constellation map, ideal signals. So ideal signals of QAM-16 constellation, which we need to have to plot. Yes, if we watch our task, so here you have it specified that you need to actually plot ideal signal positions as well. So similar as to last practical exercise when we had ideal points. Let me recall it fast for you. Like for example with crosses, and then we had these received values which were making some small clouds around our ideal points, right? So similarly, it will happen here. Yes. Okay, then, as I said, what we need to do at this moment, we didn't have any distortions or any noise, so all the points should be ideal. We can actually test that. Yes, so let us make this as a test. Real axis and has data real, imaginary axis has data imaginary, right? So grid on, and let's see how does it look. So all points should be in these nodes. Yes, so I have used plot with connecting lines. I don't want that. I'm going to rather make, I don't know, some markers, yes, instead of the lines. And as you can see here, we have clearly ideal QAM-16 constellation. So that's the only thing, however, is that we have, well, maybe, I don't know, maybe we will be able to see that. But here we have, well, if we assume the uniform generation of numbers, then we are going to have here like 10,000 divided by 16 points per each. Yes, they all are stacked up on the single position. Yes, so basically this is not a 1 point, but this is something around, well, we can actually calculate. Again, assuming that we have uniform generation, but again, we can actually try and test this with histogram. We can't test this for complex number. Okay, so this should be n divided by 16 on average, for each point will be used like 625 times, yes, if they are all equal probability points, which is the case because we have selected ourselves to use random number generator rand-e, which in fact has uniform distribution. So that means that each of these numbers is equally possible, right? Okay, so what we want to do now is to avoid plotting this all unnecessary data and display only unique points. Yes, so for that we need to calculate our constellation. So let us find QAM-16 ideal constellation, which we might need later to actually decode signal, detect signal, right? So this is map, and accordingly we are going to use function called unique that finds only unique combinations of these S-loss signal, yes, basically. So if we plot it here, then we get 16 possible values only, yes, which is true, and no other value. So this unique combination is actually something good, which we can check up, for example, to see if we have really done correctly for data real, for example. Yes, we should have here plus minus 1, plus minus 3 only. And if you can see some new number, what is not expecting, for example, I don't know, 0 here, then you know that you have done something wrong, and you can try and correct that mistake, right? So this is a nice way to test that your random generation of data is actually working as intended, right? So now, however, here I'm going to plot real part of QAM-16 map and imaginary part of QAM-16 map. I'm going to use red crosses for that. And we will not really observe much difference. Again, I'm going to use square axis as to make the scale, making these points at the same distance from one another, both on horizontal and vertical axis. So after that, you can see that this distance is now the same, which is in fact 2, right? So we might actually want to add some title, some labels and stuff like that. So sorry, 1 minute. Okay. And as a matter of fact, we should do that all at this moment. So X label is going to be a real part. Y label is going to be imaginary part. And the title going to, okay, title is going to be QAM-16 signal map. Again, we are going to add here received signal as well. Yes, so we will have 2 signals on this plot. And furthermore, in fact, we will have 1 picture for Rayleigh channel and 1 picture for Rayleigh channel, just to be able to compare them between, does it have any difference in them, right? So, signals, yes, that is correct. Now we need to make reflected signals. So we are going to have 2 reflected signals. So this is our direct line of sight signal, and these 2 are reflected signals, right? Again, actually, wait a minute. So what we are going to do now, because what I have, I think, forgotten is to apply this random value. Yes, so we have this value changing, as I said earlier, in a range from 0.75 to 1.25. But we are going to actually make some, how to say it, random process, random impulse response for each transmitted symbol. So that means that we are, in fact, going to need not one, but 10,000 values of these, 10,000 values of these, and 10,000 values of these. So let us start with generating these random values. We are going to use normal distributed process generator for this because as I, well, maybe actually I can find this because I have Ortus open. We have had this discussion on our first lecture here, yes, that in fact, if the real part and imaginary part are distributed according to normal distribution, then complex envelope, yes, which is, for example, this is data real, this is data imaginary, and this is, well, basically, for example, QAM-16 signal, which is data real plus J multiplied with data imaginary. Then the absolute value, the modulus of this complex number, is going to be distributed in accordance with Rayleigh distribution. And that is our desire, to achieve exactly that. So for that reason, we need to have a real part of the impulse of the channel impulse response. We need to have imaginary part of the channel impulse response. So let us do that. And here we are going to how to say it? Well, basically, generate. I'm going to generate random channel impulse response values for each symbol. So each symbol we transmit, the situation changes. Again, we have been talking about this on our last lecture when we discussed fast fading, slow fading, and here we assume that we have rather not really very fast, but it's still, we can say that fast fading, yes, because we can transmit only one symbol before situation changes. If we could transmit, for example, 10 symbols or 20 symbols before change, that should be something like slow fading. But here, however, the situation changes with each symbol. So we need to have 3 randomly generated columns, right? So that is going to be, first column is going to be this h mean 1 generated randomly. So let us start with it. Yes, so that would be h0 real part. As I said earlier, we are going to use random number generator with normal distribution, which speaks for this n. If you notice here, last digit is slightly different. Yes, so here we have I, which was integer. Here we have n, which is normal. Yes, and for normal distribution, if we look up on help, yes, help rand n, we can see that we need to specify only dimensions. We can also specify states, resets, and stuff like that, but there is no way to specify average, no way to specify variance whatsoever. Yes, so we will need to alter that. So if we generate this random normal process, in fact, let us do this and check it out. What is this process? Yes, rand n. We need to have n values. Yes. Let's generate it. And now we are going to plot the histogram of this H0 real. Let us say 20 bars of the histogram. As you can see, this is indeed normal distributed process, and its average is 0, and its variance is around 1. So this is a standard normal distributed process. If we want to change this suiting our needs, so that, for example, as I said, our variance would be within range from 0.75 to 1.25 with average value of 1, we need to accordingly make some modifications to this. Yes, so first of all, we need to multiply our deviation, or sigma. Yes, so basically this is standard deviation, sigma. We could have named this as a sigma parameter as well, and in fact, I believe it's not too late, so let us do that. So this is going to be actually sigma, yes, of our random process. So in order to change this parameter, so for example, right now I'm going to make the average, well, basically standard deviation of 10. Yes, now I have it around 1, but I want to make it 10 times larger. So what I'm going to do is to simply multiply our random values with this new standard deviation. And something happened. I need to use less bars, yes. So now, as you can see, our standard deviation is around 10, yes. So again, it's quite difficult to say what values of probability we need to use for standard deviations. Yes, but overall, you can clearly see that we have increased the total variance of our signal 10 times. Yes, in comparison with what it was. However, average value is still 0. This is also something we can easily change by simply specifying our own average value, which will be not random. For example, I don't know, 100. Yes. Now you should have 100 average value and different deviation of 10 from this average deviation of 10 from this mean value. So that means that we need to multiply with our h sigma, and for the 0, which is our direct line of sight current symbol, yes, component, we need to use these h mean values. So basically, and again, here, yes, we need to specify, because here we have actually a vector which is different. So I believe this was called HDiff, yes. So for the first value, this deviation is this. For the second value, the deviation is this, and for the third, deviation is this. Yes, so we need to actually consider the correct one. So for the first channel, we need to use first, and accordingly also add the first mean value. Similarly, we need to do for the imaginary part and for the others as well. So this was loss component, real part, loss component, imaginary part. And now we are going to have 2 more copies of this, H1 and H2. Yes, accordingly, here we need to specify 2, 2, 2, and here we need to specify 3. Okay, this is going to be first reflected. Accordingly, I'm going to replace it here. And this is going to be second reflected. And okay, so Now it seems that we have what we need. Yes, and what we need to do next is to actually apply this channel. So let's see what we have so far. So far, H1 real part. Well, basically I'm going to make it as a column instead. Yes, shows how our amplitude of the middle impulse response changes. So basically, this is our impulse response. This has been specified as average values for you. So that was, for example, 1. This was 0.3, and this was minus 0.2, right? So here I have specified this middle column, and you can see that this is actually a random number changing around 0.3. If I find average value of this, what I have specified, so called mean H1 real, it should be around 0.3. It is almost 0.3, but we still have some, you know, how it's called, rounding errors, yes, accuracy issues in computers, and basically, I'm sorry, for a moment, I have to watch for puppy also a little bit. So, a similar way it will work for imaginary part or any other components, yes? If we plot them into some kind of dynamic plot, you will be able to actually observe how they change in time, yes? But this is a little bit tricky and a little bit performance, how to say it, intense, yes? To actually make these plots. Maybe we will consider that for some demonstration. And again, the problem is that you will not be able to put that into your report, yes, because I don't believe PDF files can have animated pictures. So anyway, this is just see for ourselves. But as I said, we will try. Yes, it's actually possible. We may later on make some smaller program or dedicated to just this part and showing these plots. Now we have this channel, yes, real parts, imaginary parts, and now we can actually transmit our data in this channel. Yes, so this is Rayleigh channel. What we want to do now is to transmit data in Rayleigh channel. So we are going to have 3 signals: S0, direct line of sight, S1, accordingly first reflected signal, and S3. So that would be S0, S1, and S2. Sorry, yes. And as a matter of fact, the final signal, what we are going to actually display and plot, yes, is going to be S received, which is S0 plus S1 plus S2. Yes, so that is going to be our received signal, Rayleigh signal. So how do we do our filtering? Well, basically, this is some kind of filtering procedure, yes, but this time we are not going to use command called filter because each time our coefficients are changing. So instead, we are going to implement this filtering ourselves. If we plot the filter diagram of our channel, it will have 2 delay units. One delay accordingly represents travel time, and the second delay difference of travel time for the second channel. So basically, here we are having these coefficients of our impulse response. And sorry, here we don't have this output. Now we need to only add up together all these values. And we have this as transmitted output signal. Here we are going to have this input signal, which was called as loss, yes. accordingly, after this multiplier, which is H0 impulse response value, yes, this is H1, and this is accordingly H2, which are random. Yes, basically H1, H0, H1, and H2. And in fact, we need these two schematics for real part and for the imaginary part separate. But these are some details. Let us assume that there is a way to make this complex multiplication, because we can make here also complex number and multiply two complex numbers. Yes, this is doable. But I didn't really want to do that. And in fact, it's quite easy to do so anyway. Okay, then. Then here, after this first multiplier, we are going to have our signal as 0. Here, after this second multiplier, we are going to have S1, and after this third, we are going to have S2. Yes, so if we add them together, we get our transmitted signal STX. So how do we do this filtering? The filtering is done by multiplying loss signal value. For example, let us write first value of STX1. Yes, is going to be S loss 1 multiplied with H0 plus S loss previous value, which is in this case 0, multiplied with H1 plus S loss 2 values ago, that is minus first, multiplied with H2, right? The thing here is, however, that if we start counting from the first value, we do not have this 0 or this 1. But we will address this issue shortly. Let us, for the beginning, take care of this part first. Yes. So we need to calculate that for real part and for imaginary part. And that is actually going to be our S1 or S0, sorry. So the next part is going to be S1 and the next part is going to be S2. Yes. So how we are going to do that? We are going to multiply element-wise this impulse response with our real part signal, data real. And similarly, this part with our imaginary part. Yes, so that's quite simple. Yes, H0 real, element-wise multiplication with data real. That would be real part plus 1i multiplied with H0 imaginary part, element-wise, with data imaginary. So that's the direct loss signal component. Yes. So here we don't have need to access any previous values which didn't really exist yet. Yes, so no problems. Now, later, however, starting from this, the idea is quite simple and straightforward. Yes, that we need to actually change here for H1, here for H1, but the problem is that we need to access the previous value. So we are going to actually introduce some zeros at the beginning. So 1 0 here, and therefore we are going to address this and take one less value. Yes, so basically from n to n minus 1. Yes, so that this way we skip the last value of the signal just to have the same amount of symbols as in the first. Yes, so we added extra 0 at the beginning, so we have to skip the last symbol just to have the same length of the vector, right? Similarly, it goes for the second component, so this is first reflected, and similar it will go for the second reflected. There we have to have actually, oh sorry, so these zeros are introduced because of this delay line, yes? And this delay unit will introduce extra zeros. So that would be for the second component in total of 2 zeros at the beginning and 2 skipped last values. So this is basically very similar. Here we have 2 zeros. Here we have n minus 2. Here we have second impulse response. Here we have 2 zeros and minus 2. And accordingly, second reflected. Now we have this signal generated. Receive all stars at the same receiving point. Yes, so basically all these 3 signals arrive at our antenna and add up together, and that's exactly what we are going to see and receive. Okay, then, so we now can have this plot, figure 1, and don't forget that we are going to have plots for Rayleigh and Rayleigh channels. So that means that we need also subplots. Subplot 211. Yes. Let's see how it looks. Is that what we want? So here we have some mistake. I see. I didn't close the square brackets here. Yes, I needed square brackets to actually concatenate 2 vectors. This is one vector consisting only of 1, 0, and this is another vector. Here I concatenate 3 vectors, and this concatenation operation is performed by these square brackets. Now I have addressed that error. In fact, I want them to be positioned horizontally. So I'm going to make it like this, 1, 2, 1. And here I will plot later on Rayleigh channel plot as well. But first of all, let us display our received signal values. Yes, so basically these SRX. In order to see this rest crosses on top of our signal, we need first to display our received signal, then our ideal signal. So real SRX, EMAC SRX, blue or green dots. For example, blue dots. Yes. Now you can see our received signal. Yes, and in fact, it's mix it up together. No specific clouds as was before without Rayleigh channel. And this is something we should have expected. Yes, as you remember, this situation constantly changed. And I might run this code multiple times just to see how big is this difference. Yes. In no way we can clearly state that we have some specific regions of the noise. And in fact, we don't even have any noise. Yes, we don't even have any noise right now, so we should receive ideal signal, but we can't because of this Rayleigh channel. So, okay, what we need to do now is to add accordingly how to say it, Rayleigh channel model. Yes. So we have Rayleigh channel. Now we need the same way to make for the Rayleigh channel. Again, we are not going to regenerate these again, so we are going to use these results, but we need to introduce some factor of 2 for the direct loss of sight signal. Yes, because for Rayleigh channel, we have this direct line of sight signal. Yes, well, here in this particular example, we also had this direct line of sight, but this direct line of sight signal was also subject to variable level. So if I plot separately, for example, plot real, or how was it called? H0 real, then you can see that this is actually how strength of the direct line of sight signal changes. And in fact, if I zoom this a little bit, you will see that it was sometimes above 1, sometimes below 1, and it was not stable, right? Each symbol has different value, and that basically is what led us to our Rayleigh situation. For Rayleigh channel, this is not so bad situation, yes, so we need to actually consider some changes to this model, yes. So I'm going to make a copy. No copy. No, wait a minute. So this impulse response will stay. Now, the model itself will produce different signals. And in fact, I'm going to need extra plot. So this was, we might add some, I don't know, delimiting line to easier find where we start, where we end, and basically copy these results. Make sure that you are plotting this in the second signal or in the second window of the plot. And basically, if we run it now, it will produce the same results. However, we want to introduce this K ratio, right? And for, how to say, for the Rayleigh, Rayleigh channel, sorry. For the Rayleigh channel, we have the situation that, well, basically here, where we have direct line of sight signal, we have this factor 2, not really 2, but well, basically, okay, I'm going to write this. So S0 is direct line of sight, and it has a factor of square root k divided by k plus 1, additional to all what was here. Yes. So in fact, we might even skip this part altogether. Well, let's see. Well, yes, we have already this calculated, so we don't need to do that again. I assume that we can safely remove this, but because I don't want to later on find and copy it again, for now I'm just going to comment it. And then for the remaining parts of the signal, that would be S1 plus S2 and so forth, the factor is going to be smaller, which is the square root of 1 divided by k plus 1 multiplied with this. So we need to introduce these ratios. Yes, and accordingly, let us do so. So here we need square root k divided by k plus 1 multiplied with S0. And here we need, well, basically the same thing. Only we are going to replace the numerator of our ratio with 1 here, like this. So this is going to be Rayleigh. And here we also are going to have Rayleigh channel. Again, for the, oh, sorry, I think I did that in the wrong place. No matter, I'm just going to cut this out. This is still unaffected. Yes, so I'm going to put it here. Now this is going to be second plot, this is going to be first plot, and here I also want to make, in addition, for Rayleigh, basically Rayleigh channel simulation, and this is going to be Rayleigh channel simulation. So now we can probably run this script and see if it works. Yes. So it works, and well, although it's not so easy to see, but overall we can see some white spaces in between these clouds. So that means that we have somewhat started to form these clouds. However, they are not so clear yet. Yes, maybe increasing this K value to 4, yes, which was, oh, sorry, 5 was one of the tasks, yes, will change some situation to our benefit. Let's see if it is the case. And indeed, as you can see, now we can clearly see that we start to form these clouds. Yes, we have these much better. Yes, so this is the difference between Rayleigh channel and Rayleigh channel, that we might actually have better chances of decoding this signal because of the strong direct line of sight component. So this ratio basically says how much stronger is our direct line of sight compared to our how to say it, reflected, yes, all other stars. Actually, we might even simulate the situation when Rayleigh channel has no direct line at all by simply multiplying 0 here. In that case, we will have even worse situation. Yes, as you can see here, we are not even reaching the ends of our constellation. If we amplify the signal, well, the situation will be much worse. So, yes, this wasn't currently the task to simulate such worst case scenario just yet. We are not there, but we will get there eventually. But here you can clearly see that Rayleigh channel provides, well, under assumption we have this ratio quite high. I can even set, for example, 15. Yes, even better. 150 should be even better. But still, it's not going to be these, how to say it, these crosses, these specific points. Yes, and if you run this channel multiple times, you'll see that there is still some pattern change remaining. You can clearly see in my particular case this cross. Yes. Now, if we change the impulse response, this situation might actually be different. So, in fact, let us experiment a little bit. Let's take some other impulse response. Well, this is too similar. Maybe we'll take some, for example, so I have one with plus, one with minus. So let us take only positive values, right? Yes, here is positive, negative. Let's see how it will work if I make some 0.5 and minus and plus 0.25. Well, basically this pattern seems to be maintained. Yes. Now, if I reduce this one and make here, for example, 0.1. Okay, so now we have, no, I still believe I have this cross, because the points tend to concentrate more to the center, yes, and this way it looks so weirdly similar to cross. So yes, different impulse response, of course, have also effect on this, but this looks like more general thing. So I'm going to return value 5 here, and we can now make our final task of plotting the responses. Yes. So for that, I'm going to make extra separating line. And this is the task of plotting plot channel responses. So we are going to have real part and imaginary part plots, right? We need to have, how to say it, frequency response and impulse response. So first we need to plot impulse response. For real part, imaginary part, and, well, actually I believe it's better to plot for Rayleigh channel and for Rayleigh channel separately. So Rayleigh channel going to be But it's okay. Yes, okay. So for Rayleigh channel, we need to develop this impulse response of Rayleigh channel for the last symbol. Yes, so basically what we need to have, so this is going to be real part, and similar we'll have imaginary part. Yes. So this will be H0 and last value, H0, H1 last value, and H2 last value. So as it was asked in task, because each symbol has different impulse response, and the task only asks you to plot the results for the last symbol. So last symbol, impulse response, real part. Similarly, we need imaginary parts. Yes. For Rayleigh channel. And now we can calculate how to say it. Okay, wait a minute. Yes. So now we can calculate the frequency response. So frequency response can be calculated by using FreqZ. So that is Z transform. Yes. So we apply Z transform to this impulse response and basically get the frequency, the main representation of this impulse response. So this is going to be H Rayleigh. But it should be also real part and imaginary part. Yes. So that would be FreqZ from H Rayleigh real. And here we are going to specify addition. So help FreqZ. Basically, what we are using is this notation, yes, and as a result we get two values, frequency vector and absolute value. However, we are not really interested in this absolute value. So actually, I believe we might even be fine even without this one. Yes. So let's test it. Yes, this seems to be working. Similarly, we need to do so for imaginary part. And then we are going to repeat the same steps for the Rayleigh channel with some additions of this parameter, right? So basically we also will have this parameter multiplied here and this parameter multiplied here and here. So that's going to be all the difference. So last symbol, frequency response, real part. Here we have imaginary part. Imaginary part. Now we can plot all these pictures in one coordinate plane, not really coordinate plane, in one window by making 4 separate plots within that window. So let us do this. We need to have figure 2 and subplots 2 to 1, right? Accordingly, subplot 2 to 2, 3, and 4. So the idea is that the first two plots will be impulse response, and below we will have accordingly frequency response. So we are not going to be really worried much about well, basically how to say it. About x-axis units, dimensions. Yes, we are just going to use default values of sample numbers, yes, starting 1, 2, and so forth. So we are simply going to use stem function to plot impulse response. So that would be h Rayleigh real with red color, for example, grid on, and basically let us say that y label is real part of impulse response. Similarly, we need to plot imaginary part. However, numbering in window works like this. This is the first plot, this is the second plot, the third plot, and the fourth plot. So in order to have impulse response in horizontal line, we need to actually do that for the third plot here. That would be imaginary part, imag part. Similarly, we do now plot for absolute value of h Rayleigh real. This might be in blue color. Grid on, my label, real part of frequency response, FR. Well, we can actually say that this is actually AFR. AFR, amplitude frequency response for real part, yes? And similarly, we need to make one for imaginary part as well. And here we're going to have imag. So that would be for Rayleigh channel, yes? Unfortunately, I don't know of the command that can make a single title for all 4 of these pictures. I have somewhere forgotten the bracket here. Yes, usually when it says the problem is, well, in this particular case, okay, it said about correct line because I haven't closed this bracket, yes, and according that was the problem. However, sometimes it may say the problem is in line 69 and you don't even have this line 69. That usually means also that you have some brackets missing, right? So in this particular case, I have it in 2 places. So I have plotting, and here you can see that impulse response of the channel for real part is this, for imaginary part is also somewhat similar, but smaller, but greater. Yes, here we have only 1, here we have 1.5. And here you have frequency response of the particular component of the channel. That would be for Rayleigh. I don't know how to make here a title for all of these, sadly, yes. But I will look up, and maybe if I find it, I will tell you next week at the beginning of the lecture. Now we need to add last third figure to show the same pictures for Rayleigh channel. So for that reason, I'm just going to copy everything again. So this is going to be Rayleigh, 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 and here we also are going to replace everything with Rayleigh. Rayleigh. Well, basically, it was maybe easier to do like this. Yes, replace. Okay, so here is one more. Now, next, next, next. So this is our Rayleigh that it should be. Here we have also Rayleigh channel. Comment and find next, and it starts all over again from, no, sorry, wait a minute, this still should be changed. So replace, find previous, place, find previous. Yes, now we this is for Rayleigh channel, and then goes our right-hand channel. So I have not really automatically, manually replaced everything. So this is going to be third figure, and here we now need to multiply this parameter to our impulse response. That would be here these values. Here we need to multiply like this, with 1 as well here, and like this here. So that should be it. Yes, so if we run the code now, this is for Rayleigh channel, this is for right-hand channel. And actually, it doesn't look too much different. Yes. However, considering the fact that we have actually used these results and multiplied some extra values to obtain these, all the difference you can see, all that should be observable, is that by increasing the k value, this direct line of sight component becomes much better. Basically, the difference between these components is much greater, yes, as you can clearly observe from this plot. Let me actually increase this so that it becomes obvious. For example, I don't know, 25. And then it should become even, sorry, where did it go? I have lost my editor window. But okay, let me actually close it. Probably wait a minute. Yes, it moved to third screen, which is not connected, but still present in the system. That's weird. Okay, so I increased it to 25. And now you can see even better this difference has increased. Yes, so that's what is observable from this impulse response. In a matter of frequency response, this doesn't really change very much. Yes, as you can see clearly here. But then again, the difference is that, well, ideal channel should be something like constant value, like 1. Yes, and well, basically, let's make some modification to our code just to see better this difference. Yes, where we are drawing this plot, let us say that y minimum value is from 0 to 1.5. Because otherwise we have a different scale each time. Yes, and it's quite difficult to compare. Yes, so here and here. Yes, now it's much easier to see how does this reflect in the frequency response. The frequency response is much closer to flat frequency response that is for ideal channel, yes? And for the Rayleigh channel, the fading is stronger, yes? So this is actually where this fading happens, yes? So this is the fading place. Our specific frequencies of the signal are experiencing this amplitude loss. Yes, and for the right-hand channel, this fading is not so terrible, right? In fact, here we have almost constant level, almost, yes. But again, this is because I have placed this ridiculous 25 value. But for the value of 2, this is not so, how to say. But again, in fact, quite interesting scenario here. As you can see, the first value, because of the randomness, has decreased up to 0.4, which is comparable with the second value, yes? But for the right-hand channel, there still is some small difference here. Let's see how does constellation look like. I believe they should be quite bad. But no, for a right-hand channel, we can see some blank spots here, and our well, basically not really much improvement from the Rayleigh channel, but with the ratio of 5, this will become better, yes. So that's the purpose of this practical exercise, just to see what is the difference between Rayleigh channel and the Rayleigh channel, yes. So are there any questions? So today we are going to finish at this, and you can work with what time is left with this.
I have a question.
Yes.
How do we submit our practical works? Like, we just submit our script or our results, or?
So you make a small report, yes, like it's said in here, and this report should include these positions, yes. And then you send this PDF file, for example, to me by email, and I will tell you if it's okay or you need to add something else.
Okay, thank you. And one more question: are we planning maybe in the near or medium-term future to come on-site lectures?
Sorry, on second?
In the near future or mid-term future, we will come back in on-site lectures like
to the university. Currently,
yes.
Well, probably currently no, but maybe on the second part of April we may try and make some mixed, format when we will have on-site possibility, and those who can't or don't have possibility to come, yes, they will connect through Teams to join us. So I believe, yes, in the middle of April we'll start practicing this type of meetings.
Okay, thank you.
Okay, then thank you for today, and see you then next week.
Thank you. Have a nice day.
Have a nice day. Goodbye.
Thank you, Professor.